Hey everybody, Mr. Monahan here for the lesson 1-2 video. I can use the fundamental counting principle to find the number of possible outcomes of an event. So we've talked through making lists and diagrams to figure out how many ways something can happen. We've talked about tree diagrams. I'm going to show you a way that's even faster here in this lesson. All right, so when we get started here, let's look at an example from the other day. Here's another one where you're ordering breakfast at a restaurant. The restaurant has two choices of drink, milk and orange juice. We also have sausage, ham, and bacon. You're in the mood for eggs too. Your choices are scrambled or sunny side up. We want to use a tree diagram to find the number of different ways we could order our breakfast. So we started out, we've done one a lot like this already. We started out by having, we just chose a drink first. So the first one had a choice of milk or orange juice. So we said M or OJ. Okay. Then each one of those had three different meat selections that we could have used. So we went from there. And then after that, the new part for this one is going to be adding in a scrambled egg or a sunny side up. So for our meat options, what did we have? Sausage, ham, and bacon for both of them. My mistake. Bacon. Okay. Now, this is the one we made the other day. Now we're going to add on our scrambled or our sunny side up eggs. So from each one of these options, now we need two. Let's call scrambled SC and S for sunny side. Okay, so each one of these will either get an SC or an SS, and we're just going to continue to do that until our tree diagram is filled out. Okay, this part is review. This is a great way to do a tree diagram, or I'm sorry, to count the amount of possibilities for something. I'm going to show you from here a faster way, and maybe you've already figured this out. All right, so then we would go through and say there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 things in our final row, or sorry, our final column, which means there's 12 outcomes. And that would be our answer. And that's what we did the other day. We said, okay, how many ways can this happen? Let's draw a picture and figure it out. And that's great, and the tree diagram is really useful, and we'll use it for some things next chapter that will really help us out. But I'm going to show you today that there's a little bit of a better way to do this. If I know how many options there are, there's a faster way to get this done. So if I know that there are two options here, and there are three options here, and there are two options here, if I multiply that stuff up, 2 times 3 times 2, there's two drink options, there's two meat options, there's three meat options, and there's two egg options, right? If I multiply that up, 2 times 3 times 2 is 12. Now that's a heck of a lot faster than drawing that tree diagram. So that's a new strategy that we'll talk about today. It's called the fundamental counting principle. So you can fill that one in here. Like I said, right here. If you have a situation where you have multiple events like that or multiple choices, maybe you have 5 pairs of pants and four different shirts. Well, that would be 5 times 4 or 20 different outfits that you could make. So all you got to do is multiply. All right. There's situations where you can just multiply the number of outcomes of each event to find the total amount of ways something can occur. So that's going to be a lot better for us. All right, so we just did this one. All right, this is the exact same problem. Sorry, feel free to pause if you want to finish writing down that definition. So this is the same example we had started with. 2 drinks, 3 choices of meat, and 2 choices of eggs. So if I'm going to use the fundamental counting principle, I'm just going to say, okay, how many drinks were there? How many meat were there? how many eggs were there. Okay, there are 2 choices of drink, there are 3 choices of meat, there are 2 choices of eggs. That makes 12. There's 12 different ways. Okay. So we're going to go through a bunch of examples today. I'm going to have some that you're going to try, and then we'll see how far we can get. Okay, a couple is planning to have 3 children. That's an important number. Consider the different results that might occur in terms of gender. Use the fundamental counting principle to find the outcomes for the children in this family. All right, so here's what I would say. There's going to be 3 children, right? I'm going to put a blank for each event. So this is child 1 times child 2 times child 3. All right, we got to think about what the possibilities are for each one of these children. Well, they're going to be a boy or they're going to be a girl. I am pretty good at counting. I think that's 2. So there's 2 possibilities for child 1, boy or girl. There's 2 possibilities for child 2, and there's 2 possibilities for child 3. So if I wanted to figure out how many different families this could have, so I'm talking 3 girls, 3 boys, boy, girl, boy, girl, that kind of thing. There's 2 times 2 times 2, which is 8 different ways that that family can shake out as far, in terms of having boys or girls in a certain order. Okay. If you are dealt 2 cards from a standard deck of 52, how many different outcomes are possible? So there's 52 cards. Okay. You're dealt 2 of them. We want to know how many different outcomes are possible. So for this one, there's 2 cards, so there's 2 events. The first event is the first card you get. The second event is the second card you get. Okay? So for the first card, I could get any of 52 different cards. All right, I could be in a situation where I could get any single card in the whole deck, right? The second card is a little bit different because I just got a card here. Card number 1 was some card. Card number 2 is going to have to be some other card. So I can't put a 52 here again because if I'm holding a card already, there's not 52 cards left in the deck. There's only 51 cards left in the deck. So if I want to figure out how many 2-card hands there are, it would be 52 times 51. So this would be, I forgot to say this earlier, a great time to get out a calculator for the rest of this lesson. There's going to be a lot of times you're going to want it. So if you do that 52 times 51 in the calculator, you get 2,652 different hands that you could have. These are the amount of 2-card hands that are possible. Okay, let's try another one. So let's move on to number 4. How many different 7-digit phone numbers are possible if no phone number may begin with 0? Okay, so there's going to be 7 digits. I'm going to do 7 blanks right away. 1, 2, 3, 4, 5, 6, 7. We're going to multiply all these numbers up, and then we'll come at a solution after that. So we got to think about this, all right? How many different 7-digit phone numbers are possible, okay? Well, first off, we got to think about how many digits there are. So here's all the digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. That's 10 total digits, right? You can count them up if you don't believe me. So there are 10 different digits that are possible. I'm going to put 10 in for most of these. 10, 10, 10, 10, 10, and 10. There's a reason I left one out. Okay, the first number has to be something different. If you read this one carefully, it says no phone number can begin with 0. All right, well that means that my first option has to be something other than 0. So I can't have 0 for the first digit, which means there's only 9 of these left, which means I'm going to put a 9 in this column, or in this blank, okay? The reason I did that is because I know 0 is impossible. So there's going to be no phone numbers that start with 0, which means there's only 9 possible numbers, digits, that a phone number can start with. Okay, so you can do that in your calculator as well. It's going to be 9 with 6 zeros after it, which is going to be 9 million. There's 9 million phone numbers that you can make. And that's just 7 digits. That's not even taking into account area codes. So obviously there are quite a large number of different phone numbers that are possible in just the 10-digit format. Okay, let's do another one. This one says a teenager is given 5 different jobs they must do before they can go to their friend's house to watch Netflix. So the jobs are washing the car, starting a load of laundry, vacuuming, taking up garbage, putting away the dishes. In how many different orders could the teenager complete these jobs? So the jobs, they told us what the jobs were. That's awesome. What's really important is that there's 5 of them, right? Because that's what we're going to need to be able to use. So what we need to think about is there's 5 jobs. There's going to be 5 different blanks I'm going to fill. Now this one's unique, and you can see there's a vocab word coming up. This is one of the examples of what we're going to talk about next. For the first job, maybe I do the dishes first. So no matter what job we do first, there's going to be 5 options for that job. But here's the thing, if I put away the dishes already, I'm not going to put away the dishes again. So whatever choice I just used up for 5, there's not 5 options anymore for this second blank. The second blank has to be only 4 choices. There's only 4 jobs left. And then maybe you can see where this is going. After I did my second chore, now there's only 3 chores left. Then there's only 2 chores left. Then whatever's last has to be last. Okay? I'm going to show you again, right below this in a second, what this is really symboling here. So we have 5 times 4 times 3 times 2 times 1. I'm going to show you a way to punch that in on the calculator here in a second. But 5 times 4 times 3 times 2 times 1 should be 120. So there's 120 different ways that you could do the chores in order. Okay? So I'm going to pull up a calculator in just a second, but just to show you, this problem is an example of a factorial. Okay? A factorial, so know that vocab word, write that one down. It's this situation where you're putting everything in a certain order, 5 all the way down to 1. Okay? What you're looking to do is take a group of X amount of objects and arrange them in a certain way. So everything's going to get used, everything's going to be in a certain spot. So we have a symbol for this. It's an exclamation point, if you can see right here. 8 exclamation point. The exclamation point means factorial. So what it means is we're going to do 8 times 7 times 6 all the way down to 1, like we have right here. That's called a factorial. Give me a second. I'm going to put the calculator up on the screen so you can see what that's going to look like. And then we'll punch in what 0 is, because it's not what you might think. Okay? All right, so if we're looking at 8 factorial, we're going to start. We're going to have our 8 typed in there. And then different calculators will be different. So this is a graphing one, obviously. If you click the math button, and smaller calculators will have a math button too, and I want to get to this probability over here. So I'm going to go over to probability, and you can see the 4th option down is the exclamation point, the factorial. So you can hit the number 4, or you can scroll down to it, but that's where it's going to be. And then we're going to go to that exact same math menu for a lot of other things this chapter too. All right, so 8 factorial is 8 times 7 times 6 all the way down to 1. It's also equal to 40,320. So if you had 8 chores, there would have been 40,320 different orders to do those chores. Okay. 0 factorial, not what you would think. If you type in 0 and then again math over to probability, the 4th option, 0 factorial, well, that would be 0 times everything underneath it, but there's nothing underneath it. So if you type it in, you might think it's 0. It's actually 1. Just write that one down. It's not going to come back to bite us too much, but it is an important thing. 0 factorial, we just define it to be 1 so that we don't run into some other issues later with some formulas that I'll show you. Okay, so keep your calculator handy. We'll come back to it from time to time. Okay, you picked 4 numbers as your garage code. The numbers can be any number from 0 to 9. Remember that that is 10 digits. Okay, how many codes are possible? We have to start reading pretty carefully here. If you can repeat numbers. Okay, so it's going to be a 4-digit code. All right, if we can repeat numbers, we have 4 digits to pick. Let me just move that over. I don't like how I did that. If we have 4 digits to pick, we're going to multiply those numbers together. Well, if we can repeat numbers, there's 10 choices for the first digit, 10 for the second digit, 10 for the third, 10 for the fourth, because they're saying repeats are okay. In other words, you could make your code 1111 if you want it. All right, so this is just going to be 10,000. That's 10,000 different codes. It is different if you can't repeat numbers. If you can't repeat numbers, we still have 4 blanks, but let's think about how that changes things. We have 10 for our first one. We can pick any digit, but now whatever digit we just picked is gone. Let's say that the first digit was the number 2. We can't use a 2 anywhere else. So the second blank, there's only 9 possibilities left. But kind of like the chore thing, you're not going to do a chore twice. So after the 2 digits have been picked, there's only 8 options left, and now there's only 7 options left. So this one is 10 times 9 times 8 times 7. So we have 10 times 9 times 8 times 7. Okay, so that's how many options we have. So obviously it's a smaller number because we're taking out a lot of possibilities. We can't use a digit more than once. Okay, so look out for that kind of verbiage in the problems. If it talks about repeating or not repeating, there's a really specific thing that's happening there. Okay? All right, this one says, how many ways can we arrange 3 students in 3 seats? Well, 3 different students could sit here, but if once somebody's already sitting, there's only 2 people that can sit here. Now there's only 1 person that can sit here. So this is 3 times 2 times 1. Well, that's 3 times all the numbers beneath it. That's 3 exclamation point, factorial. So 3 times 2 times 1, you probably don't have to go to the calculator for. There's only 6 different ways you can do that. 3 times 2. Okay? If it's 5 students, it's 5 times 4 times everything beneath it. 3 times 2 times 1. Okay? We already did that one up here. We said that 5 factorial was 120 right here. But you could type it in again if you want the practice. That's going to be 120 different ways that the students can sit. So you notice the numbers go up kind of fast. All right, with 3 people, there was only 6 ways. By the time you're up to 5, there's 120 ways. So factorial, they end up being big numbers sometimes. Okay, let's see. How many ways can we arrange the students in the 5 seats if the middle person cannot move? Okay, well, here's what that's going to do to us. We have 5 blanks again. 1, 2, 3, 4, 5. Okay, here's the deal. The middle person can't move. In other words, there's only 1 person that can sit in the middle chair. Okay, there's only 1 person that can sit there, which means there aren't 5 people that can sit there, because one of the 5 people is already committed to this spot. Okay, which means there's only 4 people that can sit here, which means there's only 3 people that can sit here, times 2 times 1. So this one's kind of like 4 factorial, if you think about it. 4 times 3 times 2 times 1. There's an extra 1 in there, but that doesn't do anything to hurt us. This is 24. 4 times 3 times 2. There's only 24 ways to do this. Okay? These ones, if you get a word, if they give you a word and they ask how many different ways can you jumble up the letters, we don't mean actual words here. It can be really any jumbled up mess of letters. So if we're looking at the word methods, okay, every word is going to be given a place in this problem. Methods, this, just take a note, is 7 letters. Okay, so it's 7 letters long. Every different blank, I could do this as 7 blanks if I wanted. 1, 2, 3, 4, 5, 6, 7. Everyone would get a different number here, all right, or a different letter, I should say. Well, all 7 letters are going to be used, so I could do 7 times 6 times 5 times 4 all the way through. This is really just a 7 factorial problem. Okay, all 7 letters are just getting jumbled up in a specific order. So let me show you again. 7. Find your math key. That's part of your homework tonight, is to find your exclamation point, where that is. 7 factorial is 5,040. Hey, we just got that number last time we went to the calculator. Okay, so I know they're not really words, but there's 5,040 different ways you can jumble up those letters. All right, if the word is numbers, nothing's different here. This is still 7 letters. All right. Oh, you can't see what I'm writing, can you? This is still 7 letters, but now we only want 4-letter words. So now there's only 4 blanks. We're only taking 4 of the letters at a time. Okay, so for the first one, there are 7 of the letters that are available. Then there's only 6. Can't use the same letter twice. Then there's only 5. Then there's only 4. Okay, so this is 7 times 6 times 5 times 4. And that's what we're looking at here. So if we want to go to the calculator for that, 7 times 6 times 5 times 4. We get 840. So sometimes they want just a small piece. They only want 4-letter words. They don't want all of it. And again, you can't see what I'm writing. Okay. All right, so that's a lot of info. Here's what I want you to do. I want you to do as many of these as you possibly can right now, and then I will go over answers for them in a second. Now, there are some weird ones in here, so you're still going to want to listen to the video and watch me go through them, but I want you to try to think about them first. There's definitely some stuff we haven't covered quite yet, but take a second right now, pause the video, and then we'll get, when you're ready, when you've answered as many as you can, we'll go over them. All right, so hopefully you've given those a shot. We will go over them here now. Number 1, you forgot the order of your locker combo. You know the numbers are 23, 14, and 7. You just don't know which order. How many combos might you have to try to get the right one? Okay, well, if I'm guessing, I know the 3 numbers, but I'm just guessing which order. Well, I'm going to guess one of the 3 numbers first, then one of the 2 remaining numbers second, and the last number third. Well, that's 3 factorial again. There's only 6 ways that can happen. All right, hopefully you got that one. If not, that's okay. If our lockers in school go from 0 to 49, we got to think about how many numbers that is. That's really 50 digits. And no 2 numbers can be next to each other, okay, because you have to spin the dial. So 23, 23, 9 would be an example of a bad combo. That can't happen. How many combos are possible to make our lockers? Okay, so the question there is, could we have 23, 9, 23? The answer is yeah, for sure. So we can have that because the 23s aren't next to each other. So we have 3-digit combos. There are 50 digits available for the first one. The first one can be anything we want. Okay. The second one can be anything except for whatever we used first. Okay. Because it has to be something that's not the same as what we started with, so we can spin it. Now, the third one is where you might have got this wrong. So a lot of people want to put 48 right there. Well, for this one, there's still 49 numbers that aren't the same as this one. These 2 can't be the same, but this one and this one can be the same. So it seems weird, but for this one, whatever this is, say it's the number 15, This can be anything except for the number 15. There's 49 other numbers besides that specific digit. So that's why this one's a 49 and not a 48. If you put that in your calculator, I'll save you some time. 20,050. Ugh, bad handwriting. So I didn't save you much time at all. 50. 20,050. I'm going to just start over. That's embarrassing. 20,050 different combos. Okay. All right, these ones, we didn't talk about letters of the alphabet yet. Maybe you know that there are 26. How many license plates can be made with the first 3 spots as letters? Boom, boom, boom. And the last 3 digits, last 3 as digits. So 3 blanks here for digits. For letters, and we can repeat, okay? We can use more than once. For letters, there's 26 letters in the alphabet. So any of 26, 26, and 26. So it could be BBB. It could be the same letter 3 times in a row. And there's 10 digits. We can repeat. 26 times 26 times 26 times 10 times 10 times 10. That's what we would put in the calculator this time. Okay, if you do that, that's 17,576,000, and that's it, 576,000. Okay, 26 letters in the alphabet. How many license plates can be made with the first 3 as letters and the last 3 as digits? Here's the difference in this problem. If we can't repeat letters or numbers. So let's get our 6 blanks again. We can't repeat now, so we start with 26 letters, but that letter is now used. There's only 25 left, and now there's only 24 left. Okay, now we're switching to digits. The last 3 are digits. There's 10 digits for the first choice, only 9 for the next, only 8 for the last. If you were to punch that in, 11,232,000 this time. And the last one, this is a pretty basic one. A sundae comes in 3 sizes, 4 different types of ice cream, 3 different sauces, and 6 different toppings. How many different sundaes can I make if I just pick one of each of the highlighted categories? I pick 1 size, 1 type of ice cream, 1 sauce, and 1 topping. Okay, well, that's 4 blanks. There's 4 different choices we're making. And each choice is representing something else. There's 3 different sizes we can pick. There's 4 different flavors. There's 3 different sauces. There's 6 different toppings. If we're picking one of each, then this is our setup, and it ends up being 216. We can figure it out if they wanted to say, what if I want 2 toppings or 3 or more? That's just something that'll be in the next lesson. So for now, we're just worrying about one thing at a time. If you got a couple of those right, great job. I know we didn't talk about the letters in the alphabet first before we did that one. So hopefully after watching this, you can use the fundamental counting principle to find the number of possible outcomes of an event. The good news is you don't have to draw a tree diagram. You can just multiply. When you're showing your work, I want to see what you put in your calculator. So use the blanks like we were practicing here. Show me exactly what went in the blanks so that I can see if you went wrong, where you went wrong. Thanks for watching. Go ahead and try some of the practice.